The next topic is Coulomb's law. This is chapter 7.1 part 4. Previously we learnt about electric fields. As you can see here, this was what we learnt in the previous video, radial electric fields, and we learnt that this is the equation for electric field strength for a radial electric field like this. This is what we learnt in the previous lesson. So this is different from what you learned for uniform electric fields. So we have E equals Q over 4 pi epsilon naught R squared. Then we also came across this equation, which is the electric potential in a radial electric field. So you have to be familiar with these equations. Then there were some calculations. And finally we had combining electric fields. So you should be able to draw these patterns and understand that there is a neutral point here where there is no electric field. So if there is no electric field there, that means there will be no electric force there. So now we will learn Coulomb's law. By the end of this section, you should be able to make calculations of the electrostatic force between charged particles. Verify Coulomb's law experimentally. We will learn this now. Make calculations of the electrostatic force between charged particles. Charged particle interactions. And this equation is the Coulomb's law. So if you have two particles, charged particles, then the force between those charged particles are equal and opposite to each other. So if you have two like charges, there will be a force of repulsion between them pointing away from each other. And if they are unlike charges, there will be a force of attraction between them where the forces will be pointing towards each other. And let's say the charge on one is Q1 and the charge on the other is Q2, then the electric force between them is given by this equation. Alright, so let's go through this. The attraction between a proton and electron can be imagined as the proton creating an electric field because of its positive charge. Now you have learned that the electric field lines point away from the positive charge and they point towards the negative charge. So here we have a positive charge, so these arrows represent the electric field lines, and you can see the arrows are pointing away from it because of its positive charge, and the electron feeling a force produced by the proton's field. Note that it could also be thought of the other way around, with the proton feeling a force caused by the electron's electric field. A proton's field shown in 3 dimensions will cause a force on a negatively charged electron. Now even the electron has an electric field around it where the electric field lines will be pointing towards it. Like for example here, it would be the same diagram as this, but only difference will be the direction of the arrows. And here you can see this is a proton and here we have an electron. You can see the electric field line is pointing towards the electron. Anyway, this is the electric field due to the proton, not due to the electron. But even if you have an electron, the electric field lines will be pointing towards it. And like I mentioned before, this equation is very important. I can also show it to you from another book. Here we have the other book. So if you have 2 point charges, Q1 and Q2, now in this case you can see the forces are pointing away from each charged particle. So that means these particles have the same charge. If they have the same charge, they will repel each other. Like charges, same charges, similar charges. If this is positive, then this is also positive. If this is negative, this is also negative. Then only the force will be pointing away from each other, which shows that they are trying to repel each other. Then you can see here is the equation. And previously we saw that it can be written like this. So K is equal to 1 over 4 pi epsilon naught, and with that we can write it like this also. So here we have the equation F is equal to K Q1 Q2 over R squared, and if you know this, then we can write it like this also. Here we have another constant, that is epsilon naught. Now in your data sheet also this is given, so you don't need to memorize these values. But if you want the value of K, then it will be 1 over 4 pi epsilon naught. and you can see here the value of epsilon naught is this much and the value of k is this. So if you substitute the value of epsilon naught here and do this calculation, you can find the value of k. And you can also see, according to this equation, if r doubles, as long as q1 and q2 are constant, k is already a constant. So if r doubles, the force will become quarter of the value, initial value, when it was r. So if it was r, let's say the force is F, if it becomes 2r because of the square, the force will become quarter of the value. So it is inversely proportional to the square of r. We can say the force is inversely proportional to the square of r. Okay, so let's go back to what we were doing. The force between two charged particles q1 and q2, which are separated by a distance r, is described by the Coulomb's law and is given by the expression. Now remember that k is equal to 1 over 4 pi epsilon naught. By the way, this epsilon is a Greek letter. This can be seen as a logical consequence of the equations we have already seen for electric fields. Now I showed you this earlier, we learned that in the previous video also. The electric field strength, remember, if you go back over here, see the electric field strength due to a point charge or a single charge, charged particle q, is given by this. So we learned that here you can see this charge, and when r increases, the value of E decreases. Q is a constant, let's say it has a constant charge, and we went through this example also. So coming back here, we have E equals Q over 4 pi epsilon naught r squared. Now you have learned this equation previously. Remember, E equals F over Q. When we learned about uniform electric fields, we learned this equation. So for this, if you substitute this, then you get E equals Q over this. We substitute that here into this equation for E, then you get this one. So for one charge Q1 creating a radial field in which another Q2 charge sits at a distance r from Q1. So here we have both charges having radial fields around them. Note that for charged particles, the calculation of the force between them is also given by Coulomb's law, but the distance is measured between the centers of the sphere. So remember, this r is from the center of one sphere to the center of the other sphere. We can say from the center of one particle to the center of the other particle. And you can see over here also, it's shown in this diagram which we saw just now. You can see that r is from the center of this to the center of this. See, this arrow is pointing from the center of this to the center of the other one. Even here you can see that. And here you can see a statement of Coulomb's law is as follows: any 2-point charges exert an electric force on each other that is proportional to the product of their charges. See, according to this equation, the force is proportional to the product of the charges. You multiply the charge of one by the charge of the other, and inversely proportional to the square of the distance between them. And you can see over here, its whole thing is divided by or we can say, let's use this then, k, you can say q1 q2 over r squared. So here is the first part of the definition, where we say the force is proportional to the product of the charges, and then the second part of the definition, which says that the force is inversely proportional to the square of the distance between the centers of those charged particles. Then here we have epsilon naught, that is called the permittivity of free space. I have explained that in the previous video also. Note that for charged particles, now remember again, the distance is measured between the centers of the spheres. Charged spheres, the calculation of the force between them is also given by Coulomb's law. So even for spheres we can use this. For charged particles also we can use this. So this is involving two charged particles. Take care to correctly include the charge sign in the calculation of force between charges, as the sign of the final answer will tell you whether they attract or repel. Now again, from what you have learnt, you know that if two charges have the same charge, both either positive or negative, then they will repel. But if they have opposite charges, they will attract. Opposite charges, dissimilar charges, different charges, unlike charges, all those words mean the same thing. A negative force will be attractive as the force is then in the opposite direction to that in which the separation was measured. So negative force will be attractive. Now if you multiply a positive charge by a negative charge, negative times positive or positive times negative is negative. So that's what this means. If you get a negative answer for that force, because one charge is positive, the other is negative, like you can see here, the negative sign indicates they attract. But even without this, you can try to understand in your mind, if they are opposite charges, they attract. So that will give a negative answer. So you can see a negative force will be attractive as the force is then in the opposite direction to that in which the separation was measured. To understand this better, let's go through this example. Now this equation here is the Coulomb's law. So in the exam, if they ask you what is Coulomb's law, it's not sufficient to just write the equation in symbols. You also have to say what the symbols are, or simply you can write the definition that you saw over here. Okay, now if you scroll down to the end of this subchapter, the definitions would also be given there. Okay, so in this case you can see it's not given, but I showed you the definition, so you can use that definition. In the exam they can ask you to state Coulomb's law. So here you can see what is the force of attraction between the electron and proton in a hydrogen atom. So again, very simple, you can use the Coulomb's law equation, which is F is equal to Q1 Q2 over 4 pi epsilon naught R squared, or you can also write this as F is equal to K Q1 Q2 over R squared, and K is equal to 1 over 4 pi epsilon naught. Now we have two charges involved. One is the proton and the other is the electron, and they have also given the other quantities. The distance between them is 5.3 into 10 to the power of minus 11, that is R, it's given, and the charge on a proton is equal in magnitude to the charge of an electron, but they have the opposite charges, that is opposite signs. So here you can see, instead of substituting 4 pi and the value of epsilon naught, the value of K has been substituted here. Now if you go back to the values of K and the value of K and the value of epsilon naught, you can see here epsilon naught has this value, the unit is farad per meter, and K has this value, see 9.0, it's approximated, into 10 to the power 9 Newton meter squared per Coulomb squared. And here you can see they use more significant figures here. What you saw earlier, 9.0 is the approximated value, but here they are using showing more significant figures. Then you have this, so that is K. See, it's the same thing here, 10 to the power 9, so it's 8.99 into 10 to the power 9. Now Q1 Q2, you can see the same magnitude of charge, but one is positive, the other is negative, and the distance between them is that. Remember to square that, then you get this. So one is positive, the other is negative. From that you can understand they will attract each other. So if you substitute the value with the sign, you get a negative value for F, which means they attract each other. That's what was mentioned here in this sentence. Okay, so very important equation, this one, make sure you know how to use it, and very simple to use. Then we have investigating Coulomb's law. Now remember the objectives of this lesson: make calculations of the electrostatic force between charged particles. So that's what we discussed just now. F is the electrostatic force, or we can also say, some books say, the electric force. Then verify Coulomb's law experimentally. Now that's what we are going to discuss now. So here you can see investigating Coulomb's law. If I zoom this in, you can have a better look. Yes, now you can see the spheres, and this is on a top pan balance. You can see this is the scale, or the electronic scale, or maybe you can even call it the top pan balance. Now what happens is there is also a ruler to measure the distance between them, and also you can see now what is the use of this. So before we start this experiment, once everything is set up, this value is measured, or we press tar here, we zero it, then we will see what happens when this is charged. Now let's say both of them have the same charge, then what will happen, they will try to repel each other, and you can see this one at the top can't move because it's fixed to this stand. You can see here, this is the stand, this part is called the boss, and this is the clamp, so it's clamped to the stand. So the one on the top can't move. So what will happen, the one at the bottom can move a bit, because the scale, the heavier it is, the more it will move down, and the greater the reading will be here. So what happens is, when these spheres are charged, they will either repel or attract. So if they repel, what will happen, this will try to push this down. When this tries to push this down, the reading on the scale will increase, whereas if they have opposite charges, they will attract, so this will try to pull it up. So then the reading on this scale will decrease. So we can if we know the Q, if we know the charge on each, and if we know the distance between them, which you can measure with the ruler, then you can find the electric or electrostatic force. Okay, so let's see. Measuring the force between two charges, a pair of insulated metallized spheres can be charged using a Van der Graaf generator, or simply by induction using a charged plastic rod. Now you can see this and this, they are both insulated. So using, you can charge a plastic rod and keep it on this. So what will happen, the charge will move from the rod, charged rod, to the sphere, and this way you can charge the sphere. Clamping the spheres close to each other will cause a force between them, which can be measured using an electronic balance. It's also called top pan balance, electronic balance, top pan balance. By adjusting the distance of separation and measuring the force at each distance, this apparatus can be used to confirm that Coulomb's law follows an inverse square law. See also an alternative method for verifying Coulomb's law below. So what will happen now, if they have the same charge, they will repel each other, and the reading here will increase when they are repelling. Now what they do is, they bring it closer, or they move it further, they move the two further from each other. Now if you move this, now here you can see this boss here can be loosened, and you can move this clamp up, so then this will move up. So initially you can measure the distance r, and maybe you can double the distance r. Then what you can observe is what happens to the value here. So when you double r, the force should decrease by should become 1/4 of the initial value. Like that, you can check whether the force is inversely proportional to the square of the distance between the centers of the spheres. So this is how you do that. Now let's see another way we can investigate Coulomb's law, or verify Coulomb's law. Let's go through this. Everyday levitation. All materials are made up of atoms, and the outer part of atoms is considered to be the region of electron orbits. We have learned the structure of the atom. So outside the nucleus, you have the electrons orbiting the nucleus. The location of the negative charge. Why negative charge? Because there are electrons there. We can therefore imagine the top of any surface to be consist of a sheet of negative charges. So the surface of the floor and the bottom of a man's shoe will be planes covered with negative charges, because outside the nucleus you have the electrons in shells, and these electrons can get removed, or some electrons can be added to these shells. That's why they say on the outside you have layers of electrons or shells of electrons. The repulsion between these two surfaces will cause the man to levitate even so slightly above the floor rather than actually touching it. So here you can see, we can therefore imagine the top of any surface to consist of a sheet of negative charges. So the surface of the floor and the bottom of a man's shoe will both be planes covered with negative charge. The repulsion between these two surfaces will cause the man to levitate even so slightly above the floor, because you have the atoms on the floor, and around the atom, the outer layers of the atom, we can say, or shells of the atom, have electrons, negative charges. Now same thing with the bottom of your shoe, there are electrons, so the negative and negative repel. So always the man will be a very small distance above the floor, or we can say he's levitating even ever so slightly above the floor rather than actually touching it. Let's go through an example for consolidation. Estimate the height at which a man levitates. Estimate of man's weight is 800 newtons. Therefore, each shoe supports 400 newtons. So the force on each shoe, because the person has two legs, so the force on one leg or one shoe is half of his weight. Estimate of shoe surface area, so 10 centimeters by 30 centimeters. Roughly you can imagine that the shoe is 10 centimeters by 30 centimeters. Area of shoe surface, therefore in square meters, will be this much. Estimate of average diameter of atoms in each surface. Then we have this diameter of the atom, average diameter of atoms in each surface. Cross-sectional area of each atom. So we can assume the atom is a sphere, and then if you cut it in half, then you get the cross-sectional area, we get a circle. So that circle area is pi r squared. Then we have this, so area of the atom. Now they gave us the diameter, so diameter divided by 2 is the radius, so this divided by 2 you get that. And then you have the surface area or cross-sectional area of the atom, not the surface area, the cross-sectional area. Then number of atoms in bottom surface of shoe, that is area of shoe divided by area of one atom. Area of one atom means the cross-sectional area. So this will give us the number of atoms in bottom surface of shoe. It is simple mathematics, okay. Ratio and proportion is used here. Then we have area of shoe divided by the area of atom will give you the number of atom. Now this is the area of one atom, cross-sectional area. So you get the number of atoms in the bottom surface of the person's shoe. Force supported by each shoe atom. Now you know the force on each shoe is this much. So this divided by the number of atoms will give you the force per atom, that is this much, 1.51 into 10 to the power minus 16 newtons. Now let's continue. Assume each shoe atom electron repels a corresponding one in the floor surface, and oxygen with 8 electrons is the most abundant element. So estimate the force per atom that is shared between 4 electrons, with other 4 being on the opposite side of the atom at any given moment. Okay, so now if you remember what you learned for chemistry, the electrons in oxygen we can say are in 2 shells, because oxygen has atomic number 6, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Sorry, 8. Okay, so then 2 electrons in the first shell, 6 in the second shell, right? However, here now they already tell us, assume each atom electron repels a corresponding one in the flow surface, and oxygen with 8 electrons. So atomic number 8, that means it has 8 protons and 8 electrons, 2 in the first shell, 6 in the second shell, is the most abundant element. So estimate the force per atom that is shared between 4 electrons, with other 4 being on the opposite side of the atom at any given time. Okay, so you have to imagine what is happening now. Oxygen has 8 electrons, so assuming then 4 are on one side and 4 are on the other side, because if you look at the atom now, you can see only one part that is facing the flow or facing the shoe. The other part of the atom, we can imagine that it is on the other side. Okay, so because we are considering the surface of each, either the shoe or the flow. So on one side you can imagine 4 atoms out of the 8, then on the other side you have the other 4. I think it's clear. Okay, otherwise I can draw a diagram and show you, but I think you understand this. So estimate the force per atom that is shared between 4 electrons, with the other 4 being on the opposite side of the atom at any given moment. Now we already found force per atom. Now we divide that by 4 to give the force on an electron. Okay, so we have this much. Then the force on electron equals Coulomb force repelling shoe electron and flow electron. And remember this equation, the electrostatic force, and in this case it will be electrostatic force of repulsion. So we have this. Now we can find R. See, we already know this, and we know both the electrons. So this is the charge on an electron, and then we can find R. So we make R the subject of the equation, then you will have this. So levitation height equals 2.5 into 10 to the power minus 6 meters. So it's a very small distance. So the man will float a couple of micrometers above the flow surface, a distance equal to about 1/10 of the size of a human red blood cell, or the size of a bacterium such as Escherichia coli. There are a number of assumptions in this calculation, not least of which is that the positive charge of the nuclei of the atoms involved has to be considered. Also, the compression of atomic bonds within each material will mean that the force is supported across more atoms than just those considered. So this is just an estimate. So here we did not consider any positive charges. That's what is mentioned here. So this is because we assumed, that's why I told you this estimate. Also, the compression of atomic bonds within each material will mean that the force is supported across more atoms than just those considered. However, it is true that the repulsion of atomic electrons, which increase with the square of decreasing separation. So again, repulsion of atomic electrons, however, it is true that the repulsion of atomic electrons, which increases with the square of the decreasing separation. Now that is this equation. Remember the Coulomb's law equation. The force is inversely proportional to the square of the distance. From that you can understand this. Provides the majority of contact forces with which we are familiar in everyday life, and genuinely does not mean that you can never truly touch anything. Okay, so again, now we went through this investigation for Coulomb's law. Now we will see another one, verifying Coulomb's law. So the second investigation. In 1785, Charles Augustin de Coulomb published a paper in which he provided experimental evidence for the equation to calculate the force between two charges. His experiments involved measuring the force between charged spheres on a torsion or rotating balance and fixed charged spheres. A simplification of this method, which can be carried out in a school lab, is shown in figure C. Now you can see that here. Okay, so a simple method to verify Coulomb's law. Now you can see this is fixed, this we can move, so we can bring the spheres. Now this sphere is closed, but this sphere is fixed, but this we can move. So this way we can adjust the distance r between the spheres. A simple method to verify Coulomb's law. By reducing the separation of the spheres, you will see the angle of the lighter hanging ball increase. Now again you can see slotted masses or weights are attached to this, so therefore this will be vertical. But when you bring this closer and closer to this, this will, if they are having like charges, this will be repelled. So the angle with the vertical that this makes will increase the closer and closer you bring this to the other sphere. So that is what is shown here. So you have this which is vertical, the weights are attached to it, so it will be vertical. But when you bring this closer and closer, the other sphere, which is the fixed one, will get repelled. So the angle that it makes with the vertical will increase. So that is what is happening here. By reducing the separation of the spheres, you will see the angle of the lighter hanging ball increase. You can investigate the force between charged spheres and confirm that there is an inverse square law involved. So you can check that now when you bring this closer, the distance r decreases and the force increases according to the inverse square law. Now we can verify that by doing these calculations, and that the force is proportional to the product of the charges. Okay, so again verifying Coulomb's law. Figure D shows the forces on the hanging ball. So here is the hanging ball. You have the tension force and then the force of repulsion from the other sphere. Then also you have the weight of the sphere. By resolving and equating the horizontal and vertical components, we can develop a method for verifying Coulomb's law. Forces on the hanging charged ball. So here this is the length of the pendulum, or rather the string that is attached to the from the here to the center of the sphere. That is the distance. No, that is not the distance L, that is the vertical distance from here to here. Okay, because if you consider the length from here to here, it's longer than L. Okay, so this L is from here to here. So this is the line that is joining the center of one sphere to the center of the other sphere. The horizontal component of the tension balances with the Coulomb force. So Coulomb force, you can see, is equal to the component of the tension this way, because this is stationary. So the horizontal components should equal in one direction should equal that in the opposite direction, and similarly the vertical components of the forces in one direction should equal that in the opposite direction. So in other words, we can say the total upward forces should equal the total downward forces, or the total forces in the to the right should equal the total forces to the left. Now in this case, the total forces to the right equals the total forces to the left. So the component of the tension in the horizontal direction, which is T sine theta. Okay, again you can use trigonometry for this. This is the length of this, you can think is T, then you can find this side, that will be T sine theta, and that will be equal to the Coulomb force. And the weight, so we say Coulomb force, electrostatic force, electric force. Okay, and the weight balances the vertical component of tension, so that will be T cosine theta. T cosine theta equals mg. Dividing the two equations gives, so this divide by that, you can see it gives tan, because sine over cosine is tan. T cancels, so we get this. For small angles, tan theta equals d over L. So when the angle is small, you have learned trigonometry. Tan is what? Opposite over adjacent. So opposite is D. So if you look at this triangle, you can see opposite over adjacent. You will need a long piece of thread to allow this simplification to be made. So here we have tan theta, this over this is tan theta, and also tan theta is equal to this. So we can set them equal to each other. If the Coulomb force divided by mg equals d over L, then we get the Coulomb force equals mgd over L, mgd over L. Then the Coulomb force is this. Remember, we have learned this equation previously, a very important equation. That is also the Coulomb's law equation. So the F is the Coulomb's force, and we have this mgd over L. For a fixed amount of charge on the sphere, you could vary r and measure d, from which a plot of 1 over r squared against d. Now see, q1, q2, all of this 4 pi epsilon naught, all of that is constant. M is constant, g is constant, L, that is also constant, right? So yeah, so d can change, okay, d can change, and r also you can see when d increases, obviously r increases. So if you plot a graph of 1 over r squared against d, it should produce a straight line. It is very difficult to specifically control the amount of charge placed on the spheres, but having charged them both up, touching one with a third uncharged sphere can remove half the charge on each one. Doing this several times and measuring d in each case will allow you to confirm that the Coulomb force is proportional to the product of the two charges. So this is how you do that. How you show that F is proportional to the product of the two charges. Okay, so that is the end of that lesson. Now make sure you answer all these questions. I think these are very simple questions. Yeah, so you can see attraction between a uranium nucleus and an electron. So nucleus atomic number 92 means it has 92 protons. So 92 times the charge on a proton will give you the charge of the nucleus, and then electron has the same amount of charge as a single proton but opposite sign. So you can see q1, q2, you know, q1 is the charge of the nucleus, q2 is the charge of the electron, and r is the distance between them. And you can, I think you can do all these questions. Then make sure you do them and check the answers. And you should also know how to plot these relevant graphs. Okay, now if I can show you this one also. I mean, it doesn't apply just to this, but even to other cases you should know how to plot the relationship, what it will look like. We have seen some when we did electricity in the AS classes. So that is the end of this part. Now you also make sure you answer all these questions which are the end of chapter questions. Okay, you don't need to do this, but starting from here. So this covers the entire chapter 7. So we have completed just chapter 7.1, actually not the entire chapter 7, chapter 7.1. The next is chapter 7.2, which is about capacitors. So these questions here are based on the entire chapter 7.1. And remember, chapter 7.1 is divided into 3 parts: 7.1 part 1, part 2 and part 3. And we discussed 7.1 part 3 in this video, which is about Coulomb's law. So basically, just to quickly recap, what you have to know is this equation. F is equal to k q1 q2 over r squared. You can also write it like this, because K is equal to 1 over 4 pi epsilon naught. So this is the Coulomb's law, and here we have the Coulomb's law in words. Okay, the definition. And also you learned, or you saw the derivation of this Coulomb's law equation. You have learned the electric field due to a point charge is this, and then you substitute in this equation, which you first learned when you learned about electric fields, E equals F over Q, and for E you substitute this and you get the other one. Okay, so we have two charges here, two charges which both have radial fields, so we can say those are point charges or spheres with charge. And remember, R is the distance from the center of one charge to the center of the other charge, even in the case of spheres, the center of one sphere to the center of the other sphere. Then we went through a calculation using the Coulomb's law equation, and remember, F is the Coulomb's force, so it's also called the electrostatic force or electric force. And then we learned the investigation for Coulomb's law. We went through two experiments, this and also this. Now in both cases very simple, I think you can understand how it works. So here, the more the repulsion, the greater the reading here. Here, the more the repulsion, the greater the angle here. And if you plot a graph of 1 over r squared, now you can see, like I said, you should know how to rearrange it, so I can even show that to you. Now like I said, this doesn't apply only to this, so anyway I will show how you do it right now. So where is my, okay, it's origin there. Okay, so what we have here is this Q1 Q2 over I will just write K because, okay, first let me write the whole thing. So we have Q1, that is the Coulomb's force, Q1 Q2 over r squared, K Q1 Q2 over r squared. Now K is what? 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. So times r squared is equal to mgd over L. mgd over L. Now the graph they were talking about was 1 over r squared versus d. Right now you can see, I will rearrange this, so let me just move the mg, I'll write this one first. So we have what? 4 pi epsilon naught, then r is still here, then we can move the q1 and q2 down here. We are, in other words, we are cross multiplying. So we have q1 q2, then see the mg is there, mg, and the L is also down there, and times d. Now you should be able to do something like this for the other equations also. Now here you can see all of this 4 pi epsilon naught m is the mass of the sphere, that is a constant, g is a constant, q1 q2 the charges, we can say constant, you can say L is constant. So this way you can see that this is proportional to that. 1 over r squared is proportional to d. That is what is I think mentioned here. For a fixed amount of charge on the spheres, you can vary r and measure d, from which a plot of this against d should produce a straight line. So that's what I was talking about just now. Now you can think that this is the y. Okay, so this is y. So you can see this is in the form y equals mx. Now m has to be constant, so all of this is the m. So I will just draw arrows so that it's clearer. And this d is what you plot on the x-axis. This is what you're going to plot on the y-axis. So it's a graph of y equals mx. Now you know what the graph of y equals mx looks like. It's a straight line passing through the origin, which shows that one quantity, if it's a straight line passing through the origin, then one quantity should be proportional to the other. So here we have 1 over r squared on the y-axis, and then d on the x-axis. The gradient of this is what we have here. So that is what you need to know. And it is very difficult to specifically control the amount of charge placed on the spheres, but having charged them both up, touching one with a third uncharged sphere can remove half the charge at one, or charge on that one, half the charge on that one. Doing this several times and measuring d in each case will allow you to confirm that the Coulomb force is proportional to the product of the two charges. Okay, so that is what we have now. I'll just go through this book also. Yeah, so you can see the same types of experiments investigating Coulomb's law. This looks a lot clearer. Now, why is it perspex? Because that way the charge doesn't flow through this to the ground. So this keeps the charge on these spheres. The spheres are isolated or insulated. So we saw this equation previously. Then this is a Coulomb's force F, and this is a Coulomb's law equation. Then you saw that always the electric field lines point away from the positive charge, and if it's a sphere, then the field lines are radial. Okay, so just go through this summary also, and here you can see a comparison between electric fields and gravitational fields. In the case of electric fields, you have both repulsion and attraction, but in the case of gravitational fields, it's only attraction. So that's why you don't have something on top here like this. You're only at the bottom. Same thing here. So here you can see the equation for Coulomb's law, very important. This one, Coulomb law states that 2 point charges exert an electric force on each other that is proportional to the product of their charges and inversely proportional to the square of the distance between them. A point charge Q gives rise to a radial field. The electric field strength is given by this equation. The electric potential at a point is defined as the work done per unit positive charge in bringing charge from infinity to the point. So this is the definition of electric potential at a point is defined as the work done per unit positive charge in bringing charge from infinity to that point. For a point charge, the electric potential is given by this. So you have the electric field strength with this, then you have the electric potential. Now note the difference between this is, here you have R square, here you have R, V here, E there. Okay, so then we have come towards the end of the lesson, and so from this lesson, based on what you have come across, just in the comment section of this video, type what was most important that you found important. Maybe it's the Coulomb's law, maybe it's the two experiments that we went through. You can write what you learned for each experiment, then what is the permittivity of free space, what is K equal to. So this way it will help you to review what you learned, and also it will help the others who are reading the comments to review what they learned. Share the video with someone who needs it. You can also see the video description for more information. There is a link for the complete course also, and I will see you all in the next video.